Okay, cool experiment time again. This is Chapter 18. Chapter 18 really doesn't have a good explore activity for you, but I'm going to show you my own experiment, my own little demonstration. And all you need for this one is, of course, a little bit of water and a cup. And turn it over. Well, gosh, that's not very exciting. So how can we make this more exciting? Add another ingredient, which is in this case a little piece of card, just cardstock. And what I need you to do is to put the cardstock on top of your cup. There's the water. Turn upside down and let go. Explain why the water does not fall out. Why does the card not fall down? Answers coming up. Okay, so this explanation is going to use some terminology you'll be discovering in this chapter, this module. Now, what do we know? We know that the cardstock is not falling. We would expect the cardstock to fall, but it's not. Why is that? It has weight, so it should be falling toward the center of the earth, but we know that it's not. Why is that? Because there's another force acting upward that must be equal to the weight of the card. Where does that force come from? It comes from the water molecules. There's water molecules in the cup of water, obviously. Water molecules are attracted to each other. We know that. That's what we call dipole-dipole attraction. But they're also attracted to other things, including cardstock. The cardstock is uncharged, but the water molecules, the polar water molecules, can induce a charge or induce a dipole. And it's the attraction between the water molecules and the cardstock that keeps the cardstock in place. Okay, now why does the card not fall down? It turns out you're going to learn something about surface tension. The fact that water molecules like to pull on each other because they're polar molecules. They also like to pull on other stuff. And it turns out that all those water molecules are pulling on that card upward. And they're also pulling on each other. And they're able to hold up that entire weight of water. Okay, to go forward in this chapter, we need to actually go back a little bit and think about Chapter 15, Module 1, where we talked about electrons. What are electrons? It's a negatively charged sort of particle that exists outside the nucleus of an atom. And if you recall, we talked about the energy levels, or what were called shells. That electrons are approximately located in these shells. Those are the areas that they're most likely to be found. In fact, they're drawn as these like concentric spheres. Again, this is just a model. This is not really what an atom looks like. In fact, we don't know what an atom truly looks like. We only know how an atom behaves in relation to other atoms. And from that behavior, we have essentially come up with this conceptual model of what the atom is approximately structured like. The details aren't that important. It's a matter of understanding why atoms behave the way they do. So those shells are more easily represented by these concentric circles in 2 dimensions. So what we see here is the valence. Remember there was that term valence electrons. Those are the electrons in the outermost shell of any atom. So for example, they give helium here. Helium is this top upper right element in the periodic table. It is got an atomic number of 2, and therefore so it's got 2 protons, and for an uncharged atom that means it must have 2 electrons. Well, in the first shell of any atom there can be up to 2 electrons in that first shell. So sure enough, with helium, it's a pretty happy atom. It's got its outer shell completely full of electrons. Likewise with neon. Neon's the next one down. It's atomic number 10. Which means it's got 10 protons in its nucleus, and it's got 10 electrons. And it just so happens that those 10 electrons are divvied up with 2 in the first shell, 8 in the outer shell, what's called the valence shell, and the valence shell is completely full. 8 is the maximum number of electrons you can have in that second shell, and therefore neon is also pretty happy. So it's the valence electrons that are the ones that are involved in bonding or in chemical reactions. And what we just saw was what was called electron-dot structure, where we forget about all the other electrons in the inner shells. All we care about is the number of electrons in that outermost shell. Okay, now that you've gotten some exposure to the electron-dot structure, take a swing at the lab activity. It's entitled Connecting the Dots, and again, there's a little tutorial video which will help you with the interface for the exercise. Okay, once we understand electron-dot structure, this helps us to kind of get ready for how atoms interact, how they create bonds. And the most important, well, one of the important things to understand is that atoms can lose electrons or they can gain electrons, in which case they form what are called ions. Now look at this atom of sodium. Sodium is atomic number 11. That means it's got 11 protons in its nucleus. That means it's got 11 electrons in an uncharged atom. And notice how they're laid out. 2 in the first shell, 8 in the second shell, that's a total of 10, which means it's got 1 extra electron that is forced to be out in the third shell, or the third orbital. Now remember, why are electrons bound to the nucleus to begin with? Well, because the nucleus is positively charged and the electrons are negatively charged. There's an attraction there, and it keeps the electrons from flying off into space. But if you recall, if you took Physical Science 1, the force between charges is given as, there's a K, that's just a constant. It's the charge of one particle times the charge of a second particle, and then divided by the distance between them squared. So notice there is a force of attraction between this electron out here, this valence electron, and the nucleus. There's a force of attraction, but notice that there's a great distance between the two, relatively great, and therefore there's not as much force. This electron does not experience as much force as, say, this electron here, or certainly this electron here. So it does not have that much force keeping it attached to the nucleus. It could be pulled away given the proper situation. In which case, if this atom loses that electron, boom, now all of a sudden you've got a vacant shell, and now you have an imbalance as far as charges. You'll have 11 protons still, the nucleus is the same, but you've lost an electron, and therefore you only have 10 electrons, which gives this atom overall a +1 net charge. And if you've got a charged atom, we call that an ion. So this is a +1 ion. This is almost the opposite situation. We've got fluorine here. Fluorine is atomic number 9. It's got 9 protons, 9 electrons. Notice in a normal fluorine atom, we have 2 electrons in the first shell. We've got 7 electrons in the second shell, but the second shell can actually hold up to 8 electrons. So if this fluorine atom happens to be given an extra electron to fill that outer shell, now all of a sudden it's got 9 protons, 9 positive charges, and 10 electrons. And therefore we're not balanced anymore. We have a charged atom again, which again is called an ion. So an ion is not always positively charged. It can be negatively charged if the atom receives more electrons. And just in case you thought that atoms are the only ones that can have the fun in forming ions, that's not true. Molecules can actually form ions as well. So take, for example, our good old friend water, H2O, 2 hydrogens, 1 oxygen. Normally, it is an uncharged molecule. But in the presence of a hydrogen ion is a hydrogen atom that has had its electron stripped away. Remember, hydrogen is the simplest of all atoms. It's just got 1 proton in the nucleus, no neutrons, and 1 electron, normally. When you strip that electron away, you've got a proton essentially left. That's called a hydrogen ion. Now, when water, and we're going to talk about dipoles in a little while, but you can actually have water molecule combine with the hydrogen ion, and now all of a sudden you've got what's called the hydronium ion, because you now have a molecule that has 3 hydrogens, 1 oxygen, so it's H3O, and overall you have 1 extra, because it was the hydrogen ion that glommed on there, you have 1 extra proton compared to electrons, and therefore the overall molecule is not uncharged. It actually does have a charge to it. It's got a +1 charge. Therefore, this is called the hydronium ion. Okay, so now we understand that you can have positive ions. You can have negative ions. In fact, when you have a positive ion and a negative ion close enough together, they're going to be attracted to each other. Why? Because opposites attract. So for example, the sodium ion that we saw earlier, which is a positive ion. Sodium tends to lose an electron, therefore it forms a positive ion. Fluorine, as we learned, tends to gain electrons, and therefore it forms a negative ion. When you have a positive sodium ion and a negative fluorine ion close enough to each other, they're going to bond. They're going to be attracted. These two ions are going to be attracted to each other because they've got those opposite charges. So at this point, we've talked about ionic bonding. Now we're going to move on to metallic bonding. Now, one thing, let's not forget what we learned from our discussion of ionic bonding. That's a horrible look at the periodic table there. But remember that what was going on with ionic bonding, you had elements over on this side. Remember, those are metals. In fact, those are metals like alkaline metals and alkaline earth metals. And they were giving up electrons. Remember why they could give up electrons? Because they only had one or two in their outermost shell or their valence shell. And it was easier for them to just get rid of those electrons. And that allowed them to become positive ions. And then they were attracted to the type of elements that tended to pick up an extra electron, such as the halogens, the chalcogens. And these became negative ions. You had your negative ions over here, and you had, and of course, they had mutual attraction with the positive ions formed here, and you had ionic bonds. Now, one thing, remember, these are on the left side here, these are all metals. These are alkaline earth metals and alkali metals. Remember, the metals actually extend all the way across. You have transition metals and such. It turns out that all metals have the same tendency to give up electrons. The outer electrons are not that tightly bound. And that becomes very important in another type of bonding called metallic bonding. So with ionic bonding, usually it's metals and nonmetals. But you can actually have metals bonding to metals via metallic bonding. Because essentially what happens is the electrons are the outer electrons are allowed to move quite freely when you're dealing with metals. And what that does is that allows for many metallic properties, such as conductivity of electricity. You know, most metals are good electrical conductors, whether we're talking about aluminum or gold or copper. And that's why the wiring in our homes is copper. The reason being electrons. The motion of electrons is what we know as electricity. And the actual bonding of one copper atom to another copper atom, quite often the outer electrons are allowed to move around very freely. And it's that motion of electrons that we call electricity. So metallic bonding, one of the features of it is that it has a lot of freely moving electrons. And therefore, that's why metals are shiny. That's why metals are good conductors of electricity, as well as good conductors of heat. Okay, so we've already talked about ionic bonds, and those typically occur between metals, especially the extreme metals, alkaline earth metals, and nonmetals. We've also talked about metallic bonds. Now, metallic bonds can occur quite often between metallic atoms. If it's gold and gold, it's just a metallic bond. If you have gold and platinum or something like that, two different metals, we call that an alloy. But that's within the metals, is typically where you have metallic bonding. Now, covalent bonds quite often are bonds that form either within nonmetals, or it can actually also occur between a nonmetal and hydrogen, as we're going to discover. Because hydrogen, even though it's listed as an alkaline, alkaline metal, it's kind of loosely a metal. Under the right conditions, it acts like a metal. In other cases, it doesn't. But covalent bonding occurs because atoms are sharing electrons, not just giving up electrons, but actually just sharing electrons. So, for example, fluorine. Remember, fluorine has an atomic number of 9. Which means it's got 2 electrons in the first orbital, or the first shell, and then that would mean 7 electrons in the outer shell. Of course, the outer shell wants to have 8. And so, one way that 2 fluorine atoms can satisfy their outer shells is by sharing an electron. We're actually sharing a pair of electrons, turns out, because each one contributes one outer shell electron to the coupling, and they form a covalent bond, in which case, now notice each atom has its full complement of electrons, 2 in the first shell, and then a total of 8, right? 2, 4, 6, and with the shared, this guy has 8 electrons in its outer shell, and same thing with the other guy. So you have 2 happy atoms that are now bound together because they're sharing a pair of electrons, and therefore we call that a molecule because it's more than one atom. It's a fluorine molecule, and we list it as F2. So the 2 electrons are a covalent bond. That shared pair is what we call a covalent bond. And quite often in an electron-dot structure, that shared pair of electrons is represented as a straight line. And notice that quite often we don't have anything listed here. Those non-bonding electrons are not even listed. They're just assumed to be there. So the only pair that we really care about are the pair that are being shared in the covalent bond. So let's take another example. Oxygen and hydrogen. Remember, hydrogen has a proton and an electron. And the first shell of a hydrogen atom wants to have 2 electrons. So notice the hydrogen atom has 1 electron, it wants 2. Same thing with this hydrogen atom. Now think about oxygen. Oxygen has atomic number 8. That means it's got 2 electrons in its first shell, not even pictured here. It's got 6 electrons in its second shell. Here's 2, here's 4, here's 5, and 6. Now notice if this hydrogen atom would share its electron with the oxygen at that position, they could both be satisfied. And same thing here. So if we have the sharing going on, now notice that everybody's happy. The hydrogens have 2 electrons in their first shells. The oxygen has 8 electrons in its outer shell, and it's happy. And that's what we have. We have water formed there because now we have a water molecule where 2 hydrogens are covalently bound to an oxygen. Same thing with ammonia. Ammonia, similar situation. Again, we've got hydrogen at work here. Hydrogen, it's got 1 electron. It could, it's not really much into ionic bonding because it's tough to pull that electron away from, the hydrogen is so close to completing its shell. So therefore, hydrogen would prefer to share if at all possible. And that's sure enough what happens with the nitrogen. By sharing electrons between 3 hydrogen atoms and the nitrogen atom, you can make everybody happy, and you wind up with ammonia and H3. And one more, methane, right? Natural gas, same thing. Notice the carbon is atomic number 6. It's got 2 electrons in its first shell, 4 electrons in its outer shell. It's got 4 places where it could share an electron, and sure enough, that's what it does. It forms covalent bonds with 4 hydrogen atoms, therefore creating methane CH4. So you can have multiple covalent bonds. And when there are multiple covalent bonds, instead of just a single line, you'll actually see double lines or even triple lines, depending on how many pairs of electrons are shared between the atoms. Now that you know the difference between ionic, metallic, and covalent bonds, put your knowledge to the test, go into your skills test, and take your swing at the types of bonds activity. And again, as always, there's a video tutorial that will help to step you through the quiz and get you familiar with the interface. Okay, since covalent bonds are all about sharing electrons, think about sharing. Think about sharing if you have children or if you've dealt with children before. Quite often, children may share, but they don't share evenly. So let's say you got 2 4-year-olds. They might be at the same level and capacity of sharing. And so if they're sharing a toy, they might each spend the same amount of time with the toy, back and forth. That is very similar to this situation where 2 hydrogen atoms are sharing a pair of electrons. And the electrons tend to spend, that shared pair tends to spend most of its time smack dab in between the 2 hydrogen atoms. So there's a equal amount of sharing. But what if you have a 7-year-old and a 4-year-old? They may share it, but this 7-year-old probably will have the toy a little more than the 4-year-old might. That's what goes on when you have unequal or different types of atoms sharing a pair of electrons. It turns out that fluorine, because of its larger atomic number, it's got more positives. It's got a more positive nucleus, and therefore it's going to attract an electron more. It's going to be a greater Coulomb force with the nucleus and a shared electron pair. And therefore, even though there's a shared electron in here, shared pair of electrons, it's a little closer, spends a little more time with the fluorine atom than it does the hydrogen atom. And so notice with this overall atom, and of course all these dots are indicative of electrons or possible electron locations. It's the electron cloud. The electron cloud seems to be shifted a little bit to this end of the molecule, which would make this end of the molecule somewhat negative, because the electron tends to spend more time over here, and it would make this end slightly positive. It's an uneven sharing of a shared pair of electrons that we call a polar covalent bond. Because it's covalent, it's a shared pair of electrons, but it tends to make one end of the molecule negative and makes the other end of the molecule positive. The tendency of an atom to want to be greedy about sharing electrons is a term called electronegativity. And there's actually a chart on page 399 that will show you the electronegativities, the tendency of various atoms to pull on electrons. And the lower the number, the less greedy; the higher the number, the more greedy. And therefore, you'll see that the halogens like fluorine and chlorine and bromine, those have very high electronegativities because they're so close to filling out that outer atom, or that outer electron shell. Whereas the alkaline metals, the alkaline earth metals, have relatively low electronegativities. They really don't want to hold on to atoms. They're more likely to give up an electron than to want an electron. Okay, so here we have pictured three different types of bonds, really. We have an ionic bond between sodium and fluorine. Remember, it's sodium and fluorine. It's a situation where essentially the sodium doesn't want its extra outer electron. Fluorine is really, really close to completing its outer shell, and so essentially sodium will give an electron to fluorine, therefore producing a positive ion for sodium and a negative ion for the fluorine, and of course that those opposites attract, and you wind up with a sodium fluoride molecule. With hydrogen and fluorine, they both want to be satisfied. Hydrogen is close to completing its outer shell, because of course it only needs 2 electrons in its outer shell. It doesn't want to necessarily give up an electron, but it would much rather share. And sure enough, fluorine is a good partner to share with, because fluorine needs 1 electron to complete its outer shell. So they wind up sharing a pair of electrons. But again, fluorine is a little more greedy. The electrons spend more time on this end of the molecule, and therefore this end becomes slightly negative, and the hydrogen end becomes slightly positive, and therefore you have a polar covalent bond. They're sharing, but it's an unfair sharing. And as we've already seen, between fluorine and fluorine, they share a pair of electrons as well. So it's covalent, but notice this is non-polar, because the electrons do not spend any more time with one fluorine compared to the other. Okay, so now we know that there can be an unfair sharing of a shared pair of electrons between 2 atoms. But what if we have more than 2 atoms? What if, in this case, we have carbon, which shares a double covalent bond with oxygen, but actually in CO2 it occurs on both sides. So we have the oxygen, which pulls more on the electrons than the carbon does, because it's closer to finishing its outer shell. It's got a higher electronegativity. So you wind up with this oxygen pulling on the electrons in this direction, and this oxygen pulling on another pair of electrons in this direction. But overall, that pulling tends to negate itself. We have a tug of war here, but the tug of war is an even battle. And therefore, the overall molecule is not polar. The polarity cancels itself out. So this carbon dioxide is not a polar molecule. It does not really show any polarity. But that's not the case of water. Think about water. What's going on? Again, you have a hydrogen two hydrogens sharing pairs of electrons with oxygen, but notice the geometry is different. Instead of being lined up in a nice straight line, there's actually a bond angle here. And so sure enough, the oxygen pulls on each of these pairs of electrons more than the hydrogens do. But notice in which direction, kind of upward in this case. So therefore, you have a negative end of the molecule and you've got a positive end of the molecule. So water, H2O, is polar. So H2O is polar, whereas we just saw that CO2, not polar. And that polarity is very interesting. It can produce some very interesting results. Think about the fact that we've got a negative end of a water molecule, we've got a positive end of a molecule. Wouldn't the positive end of water molecules be attracted to, let's see, another negative? For example, couldn't water molecules be attracted to each other? Couldn't the negative end of this water molecule be attracted to the positive end of this water molecule? Sure enough, that's the case. And that's why that leads to things like surface tension in water, which you might want to read up about. That's why, like, water striders can walk across the water. Another example is the high boiling point. The fact that water molecules tend to cling to each other, they're attracted to each other because one has a negative end and one's got a positive end, affects the boiling point of water. And it also leads to other cool phenomenon like being able to bend water with a balloon. Check out the next video.
Okay, here's another neat demonstration you can do using static electricity. Notice what I've got here. I've got a little stream of water. And that stream of water is, of course, falling downward. Why? Because water has weight and the earth pulls on it downward. But what happens, remember when I did this up with my head? And I charged the balloon, I scraped electrons off my hair, put them on the balloon? What do you think's going to happen if I bring my balloon close to that stream of water? Remember, that water's falling downward. Why? Because there's a force acting on it. But now all of a sudden, what happens? Can you see that? My balloon gets wet. But notice that the water bends. Right? Water doesn't bend just because it wants to. Water bends because it's being forced to.
Okay, now we're moving into section 18.8. It's entitled Molecules Are Attractive. When you're reading this, pay very close attention to that highlighted section. And it's such an important point that they even, on page 405, put out a little reading check. Make sure you understand that when we start talking about the attractions between molecules, and there's several different types, starting out with ion-dipole attraction, that those attractions are still much weaker than the attractions that make the molecules themselves. For example, water, there's H2O, salt, sodium chloride. And we know that H2O is a covalent bond. Remember, there's covalent bonds here between the hydrogen and the oxygen. So this is a example of covalent bonding. Sodium chloride, ionic bonding. The attractions between the sodium and the chlorine, the attractions between the hydrogens and the oxygens are much stronger than the attraction of the water molecule as a whole to the sodium chloride. So that's one thing that's very important for you to understand. However, there is an attraction. The fact that in the case of water, remember we've talked about the fact that it is a polar molecule. It's got a positive end, it's got a negative end. And sure enough, the negative end of the water molecule will be attracted to the positive ion of sodium, positive ion that makes up the sodium chloride. Similarly, the positive end of a water molecule is going to be attracted to the negative chlorine ion. And when you have the cumulative effect of a lot of these attractions, you can have essentially a dissolution or create a solution, an aqueous solution. Okay, so that's what we talk about dissolving. When you put salt into water, the salt will dissolve. The water molecules will attract those ions that make up the sodium chloride. Okay, we've also talked about the attraction that one water molecule has with another water molecule. Remember, the water molecule has a positive end, it's got a negative end. And when it gets close to another water molecule, again, these individual bonds, the bonds that keep the water molecule together, are much stronger than any kind of intermolecular bonds, or attractions. But there is going to be an attraction. You've got a positive end of this water molecule being attracted to the negative end of this water molecule. And that's called a dipole-dipole. Each of these are dipoles. Each of these are polar molecules. And therefore, the attraction we call a dipole-dipole interaction. Okay, to explain the third type of molecular attraction, the dipole-induced dipole, I want to do a quick little demonstration. And notice I've got a balloon here. It's kind of a weird balloon. It's an odd-shaped balloon because it's an old balloon. But notice what happens when I say put the balloon on this computer screen. Nothing, right? There's no attraction there. However, notice what happens if I rub the balloon in my hair. I'm going to essentially scrape electrons off of my hair and into the balloon, or onto the balloon. Notice how it stands up, right? So I'm creating now a charged balloon. I've got I'm going to make a negatively charged balloon. So pretend this is like the negative end of a polar molecule. And I'm going to bring this negative balloon now close to my computer screen. Notice what happens now. It sticks. Why is that? Because the negative balloon, when I brought it close to that screen was uncharged, had positives and negatives. The negatives were repelled by the negative balloon. So they went further into the screen, which left the surface, it didn't get rid of the electrons, they just moved in just a little bit. And without those electrons being close to the surface, now the surface was just left with protons, positive charges. And therefore the surface appeared to be positive. So I essentially made the screen, which was uncharged, I made this screen sort of become a dipole because the positives were left at the surface and the negatives got shoved in just a little bit. So I created a dipole. I induced a dipole. I made the screen slightly positive at its surface, and therefore I've got a negative balloon close to a positive screen, and boom, I get the attraction. So that is a dipole-induced dipole attraction. Okay, if you like that one, you'll like this one even more. What I've done is now I've got my cup, empty cup, and what I've done is I've put a little bit of tulle. Do you know what tulle is? Tulle, that really fine, meshy fabric. Can you see that? Got a little bit of tulle on there. Now what happens if I pour water into my cup with the tulle on top, and I turn it upside down? Not surprising. Okay, now let's try one more thing. Let's do the same thing, except let me put a card on top here, and let me slide my card out. Ha-ha! You see what's going on there? The water doesn't fall out. The question is why? Can you figure out why the water is still in the cup? To explore how the mesh holds up that water, let's just take one cell of the tulle as an example. So what we have, we've got water molecules, and those water molecules are going to be attaching to the tulle via a dipole-induced dipole attraction. But we've also got water molecules kind of out in the middle of the grid. So what's going on with them? Remember, you can't forget about dipole-dipole attraction between water molecules. They are all polar. And so they kind of link arms and hold each other up. They're bound to each other through this dipole-dipole attraction. And it's that combined effect of all those linked arms which overall provide enough force to keep the weight of the water up so that the water does not fall through. Only when I disturb this dipole-dipole attraction does the water fall out. Okay, so this last type of molecular attraction, this dipole-induced dipole, is relatively weak, but it's very important, especially as your book details on page 407, when it comes to dissolving oxygen in water. And if it wasn't for dissolved oxygen in water, fish wouldn't survive. So what is actually going on? We know that oxygen, O2, is a nonpolar molecule. It's got a double covalent bond between two oxygen atoms, and they both have equal electronegativity. It's a straight line kind of bond, and therefore there is no polarity here. It's a nonpolar molecule. But bring that nonpolar molecule close to a water molecule, which does have, it's polar. It's got a positive end, it's got a negative end. And what's going to happen is the electrons of the oxygen molecule are going to be repelled in this direction. And therefore, you're going to have a negative end, and then of course then the other end is going to appear somewhat positive because the electrons have essentially shifted. And so you have induced a dipole. You've taken a nonpolar molecule and created a slightly polar molecule out of it just by its proximity to another polar molecule. And now you can have the attraction between the positive end of the oxygen and the negative end of the water, and that is your dipole, induced dipole. That allows the oxygen to dissolve in the water. Now remember, it's very, very weak. So there's not that many oxygen molecules on average that wind up dissolving into the water, but there is enough dissolved oxygen in water to allow fish to survive. Your book doesn't really get into it, but there's actually technically a fourth molecular attraction, which is an induced dipole type of attraction. And you need to have two nonpolar molecules, for example, argon. We got two atoms of argon here. They're nonpolar, but the random motion of the electrons can sometimes result in something like the electrons grouping to one side of this nonpolar molecule, in which case you would have a temporary dipole. And of course, those temporary dipoles then could induce a temporary dipole in a nearby atom or molecule, and therefore they would be attracted. Again, these are relatively weak. The larger the atom, the stronger the momentary dipole. But in general, of these different intermolecular attractions, the induced dipole is by far the weakest. Okay, so now that you know all about polar molecules and intermolecular attractions, test yourself. So remember the different, first of all, how a molecule can either be polar or nonpolar, quite often depending on its geometry. That's going to be useful. And then also think about the relative strengths of various intermolecular attractions and take the polarity skills test. Again, there's a little tutorial video that goes along that will help you step your way through it. And finally, these are the Readiness Assurance Test answers for Chapter 18. Again, you'll find these at the end of Chapter 18. Looks like it's on page 412. I'm sorry, 410, 411 of your textbook.